appreciate your time today. We're obviously going to be talking about casting simulation and hopefully through a customer story explain how it's really used in real life real life practice. I'm Rob. I look after the sales and marketing side of Origin. I certainly won't be doing a lot of the talking today, apart from a brief introduction, but I will be your point of contact moving forward if you do want to chat with us further. Really pleased to be joined by my colleague Tim Dukes, who heads up the support and training functions at Origin, but also pretty involved in the pre-sale side in terms of demonstrations. So he'll be speaking a bit later on. It's fair to say, I think that the real star of the show is Mike from Skaigh Engineering. He's part of the management team there. And from our perspective, we're just really lucky to have a customer actually talk about their experiences. I think for most of you on the call, listening to how it's really used is more important than perhaps listening to what we think of the product. So a big thanks to Mike, and look forward to hearing from him a bit later on. Brief introduction, just a couple of minutes from me. We'll then pass over to Mike to take you through that customer story, and we'll finish off with a quick demonstration, actually showing you how we set up some examples and take you through a couple of different options there, show you how we can interpret some results as well. So as Pete said, we prefer the sessions interactive, so do ask questions and we'll make sure we get to them towards the end. There'll be plenty of time for them. So in terms of Origin, we've got around 200 customers. I think what's unique about us is we are really focused on the manufacturing space in terms of really targeting design and manufacturing engineers. I guess you could say we're trying to advocate for using simulation more often, earlier, and providing those simulation tools to more people in the business. We provide software support and training here in the UK, where all of our customers are based. The solution that we're showing today is from Altair. We partner with Altair. I mean, obviously we like the technology. We think it's good technology, but we also think it's quite affordable. We think that the interface is quite clean. It's quite easy to use, and it's quite easy to train people on. So a lot of our customers are sort of SME businesses, which it's really important to get people up and running quickly with the software, and hopefully you'll see that a bit later on. That's enough about our company background, but as I said, we do believe that simulations should be incorporated much earlier in the method engineering workflow or the part design workflow. We know that many organizations may do it, but we often question, at what stage are you doing that simulation? Are you doing that simulation of the method right before manufacture? Are you doing it perhaps after you've got prototypes done? We think if you do it right early on in your design process, you can unlock some of those benefits. The most obvious benefit is obviously spotting defects earlier that we associate with casting. So being able to eliminate failed production runs, or being able to eliminate the cost of perhaps potentially buying in some soft tooling to realize that the method actually doesn't work, and then you've got to go back to the drawing board. Because we know, actually, if we look at the cost of design, it is often earlier on in that process where a lot of the time's spent. And the longer down the track you go, it becomes harder to correct mistakes. It becomes more time consuming. Yet actually, when we look at how simulation is being used, typically it is at the end. It is right at the end. So we want to push that back a bit earlier and give it to more people. As well as eliminating defects, we can obviously allow designers to explore multiple concepts, multiple ideas, different gate positions, different techniques, different materials, and we can allow them to do that in a safe space. Often we find that in the absence of simulation, in the absence of validation, you do tend to over-engineer a method to make sure it's safe, to make sure you get it right first time. So hopefully we can allow more concepts to be explored quicker and lead to better outcomes. I'm, sales and marketing. I've said that at the start. So what's important for me is also being different and differentiating myself amongst the competition. And we find that customers that perhaps have a client come up to them and say, we need that part produced. If we're able to actually go to them and be able to show that we've actually simulated how that part is going to be produced, we've simulated what our casting method is going to be, we've simulated and we've validated the fact that we expect that part to be produced free of defects, we think that company is a lot more likely to win that work than someone that hasn't used simulation. So I think for me, simulation isn't just a validation tool, it's also a communication tool, and it can be used as a way to win more work. So before I pass over to Mike, I think it's useful to share some of our observations in terms of what we see happening. I think the most obvious one is that the workforce is getting older. People often say that casting is a bit of a black art. The knowledge is in the brains of a select few that have honed their skills over many years, and rightly so. Those organizations trust them to deliver a quality product. But as those people leave the business and graduates join, it really is impossible with the best will in the world to transfer that 30 or 40 years worth of wisdom and knowledge to someone that's just starting out in the career. So we think simulation can hopefully supplement that. It can bridge that gap between knowledge to allow the people coming into the business to take that business forward. And actually, if we look at graduates, if we look at their day-to-day lives, number one, most of them would have been taught simulation at university. Number two, people are used to using applications to validate their decision making. So actually using this software, it's not alien to them. It's kind of what they expect. It's kind of what they prefer to do. So, we hope that simulation can ensure quality, enable better productivity, but it can also actually help to future-proof that business. When those more experienced people leave the business, there is something going forward. I think the final thing is that we are seeing that as technology improves, we're pushing the boundaries of what we want to produce, and the complexity of the parts is increasing. Designing the correct tooling could be more challenging. So we think having simulation there definitely helps. Not only that, the customer expects more. They want lead times to be lower, delivery times faster, and costs lower. So anything that we can do to stay competitive is really important. So in terms of what you're seeing today, it is the casting simulation product. Before I pass over to Mike, it's just worth you being aware that the casting simulation forms part of a product suite, and you get access to all of those products. So if you are on the call today and actually do other things but just casting, perhaps you do some metal forming, perhaps injection molding, maybe even 3D printing, FEA, fluids, there are tools within that product suite which may help you. So at the end, feel free to reach out to us about that. So what I'm going to do now is I'm going to pass over to Mike. So Pete, if you'd like to pass over to control, we'll just give Mike a minute or so just to get set up.
Yeah, thank you, Rob. Mike, control should be with you, and we can see you slide now.
Just unmute yourself when you're ready, Mike.
Sorry about that, guys.
It's okay. Right. Off you go.
Right, little resume about myself. I've been in all my working life in the foundry industry. Had many job roles. Started as a trainee methods engineer. Had to do pattern making and technician apprenticeship. Went out as a foundry consultant. Had the ability to teach methods engineering, not only in England, but parts of the world. Being a foundry manager at a few companies, technical manager and a vice president of production. Worked in many materials, cast irons, your SGs, your grey irons, very various amount, different types of steels, aerospace alloys and non-ferrous alloys. Having worked in an aluminium foundry in the past and joining Skaigh Engineering as a foundry manager, I always wanted to have a simulation tool, because in the past I've used Magmasoft, Procast, SolidCast, and all the good pieces of software. However, we chose for our use in the gravity die casting to use Inspire Cast. Just a little bit about Skaigh Engineering. We was established back in 1965 by George Ripley. Since July 2020, I came on board as a director with Tessa Shaw, Matt Edmondson, and Nick Newman. And we're trying to push our foundry into the forefront and be a competitive foundry like the rest of you guys. We employ 28 people, and we are putting investment in our foundry. And one of them, like I say, one of the main investments is to have casting simulation. Like I say, I've had 44 years of foundry education experience, and we have a good apprenticeship program, and I need to pass that on to one of our employees in a few months' time. And casting simulation is a good tool. We manufacture aluminium gravity die castings for a wide range of companies across the UK. Several grades of aluminium and zinc. Our casting batch size is 5 to 1,000 components, weighing from 100 grams to 30 kilograms. We're quality assured. We have on-site facilities. We have a tool room. We manufacture shell cores. We do our own heat treatment. We do offer surface finishing that is done off-site. We also have our own machine shop, and obviously we offer casting simulation as a problem solver and also on customer new designs. So what I want to talk to you guys today is on 3 case studies. One on an actual die casting, one on a new product we've took on board, which is a bleach and beaker halo, and a problem solving on a die casting housing. Right, before I get there, right, what we were like a few years ago is we were good at inheriting people's dies. You know, they've gone around the country, they've gone from foundry to foundry, and we get that die and we have to cast it. So we cast a sample off, and it's always the same. Your sample's always good the first time. Then you go into manufacture and you have a high scrap rate. So obviously you've priced that up to a customer. It's very difficult to go back to a customer and say, right, the scrap rate's this, what do we do? And again, you don't know what that die is going to do, but if we've got it and it's gone around a lot of foundries, we're getting poor quality. Hence, increased costs. We find that we get excessive fettling. The gates are not in the right situation, so it's taking time to remove the gates to get back to that near net shape. High scrap rate, might be full of shrinkage, gas porosity, all incurring costs that we can't pass on. And again, long lead times, because if we can't make it, we've now got to spend a lot of time looking at the die, doing sample trials out in the foundry to get where we should have been right at day one. And we always want to do research and development, but doing trials in gravity die is not cheap. You're having to send the die into the tool room, do a trial, cut metal out, not helping the die properties because now you've weakened the die. So it's so hard to do development in a gravity die casting, and we're relying on people's experience on the shop floor, myself and other colleagues. So bringing simulation on board, right, it does reduce the sample time. It's quicker to design. You can work with the customer. You can go from concept, simulate, put your techniques on, look at problems that lie on the part. You might have isolated junctions or sections. Increase quality. You know, if you put it through the simulation tool and it's not showing any indications, you know that the method's correct. What happens on the shop floor is down to your quality control and your assurance. but at least you know you've got the technique right, and so you can problem solve elsewhere. Again, less wastage. It enables you to think out of the box. You can try different manufacturing techniques, different gating techniques. For us, we look at also die section thickness, because that also influences how our casting solidifies. So we can experiment that before we go to the final design. Also, education and awareness, right? This is good because we do share these results to the shop floor. So if we're looking at an existing product, we'll invite a guy from the shop floor who makes that or pours that die, and he might point out something we haven't put as in the data set, and then we can re-simulate it. So we're trying to get to what we're actually doing, pure, proper physics. And again, knowledge, able to interrogate fluid flow and solidification and get accurate problems we can solve out. Right, I want to talk first of, we've got a worn out die, we have a good customer relation, and we need to manufacture a better die. Now, I don't know if it happens in a lot of gravity die casting foundries, but a lot of foundries allow the tool maker to put the manufacturing technique on. Saying that, this particular product is an air actuator, and I've got a schematic model down on the page showing you that we've got core plugs, a 4-part die, and you've got the product and the method of manufacture. This die lasted for 15 years. It made 19,000 saleable parts. However, we must have put actually 24,000 pours into that die, or maybe even more, because we started incurring a lot of scrap rate. With that die, and I'll show you the simulation shortly, is we relied a lot on the shop floor, tilting the die in different orientations to get a correct pour. And we decided with our customer, the die had worn excessively. In the right top corner, you can see the die. I wanted to magnify that, but I do apologize. My software's not allowing me to do that. It would show you a lot of metal erosion over time. Hence, you know, you get large die lines, flash lines that have to be removed. So what we wanted to do is improve the die design. So we started up from the basics, and that was, let's simulate what we currently do. So this is where we're tilting this around about 20 degrees. You can see that we've got 2 metal streams. Not the best technique, but I've got to show you warts and all. From that, obviously, we can improve that. So we've got a proper pouring base and a good target area for the pouring guy to pour into the well. So actually the gating system is controlling the fluid flow. We're not relying on the pourer. Obviously we've got to rely on the pourer, because he's got to pour at a steady state into that pouring basin and make sure he gets the right level of metal. But as you see, the metal goes down. We've got it very controlled. Nice wide ingate there to get a nice laminar flow. So yeah, we can see we've got a good flow happening. Or levitating or gravitating back into the feeder. So yeah, we've got a good technique. Where do we go from there? Well, in Inspire Cast, there's a great tool, especially for a die casting foundry, because you're only looking at the fluid flow. What you actually need to do is, in a gravity die, it's not like a sand mold where you've got permeability. You've got solid metal sections, and you've got to evacuate the air. So what we can do in Inspire Cast is we can look at the air being removed out the die. So from the predicted outcome, you can see on the left-hand side, we have bosses on this actuator part, and that's where we're going to get air entrapment. That can be in the form of a gas bubble in the metal, or if it's trying to get out through the cast section, and get entrapped in the solidification, or we can get a rounded, cold sort of surface on the edge of the casting. On the right-hand side, also, you can see that we've got, even though we've got a little gradient in the casting, we've got air entrapment on top of the barrel. So the solution, right, is now we go to talk to the tool maker and we can put a vent into the die. Obviously, I've shown you where we've positioned it. We can't put it ideally to the top of where that radius is because that weakens the die, but we can sufficiently put it where we need it, where it doesn't affect the die performance or cause a problem with the die, and we've now removed that. On the one on the right hand side I showed previously, we would put the vent in on the core plugs. Also, what we can do is we can do a validation about the soundness, and we can do a virtual X-ray, and we look at macro shrinkage. So on the left hand side, on the prediction, in the little red regions, that is predicting macro shrinkage. I'm not worried about that because you can see in the top wireframe model, we have macro shrinkage in the feeder and in the lower part on the running system. We always validate, like most foundries, we cut castings up, and on the right hand side, that shows you the section illustrating that that casting had no macro shrinkage. With aluminium, not only macro, but I could say that with a lot of cast materials, we need to look at micro shrinkage. I have to go on my soapbox here. Please do not use porosity, because porosity means a multiple of sins. When you're predicting the right defect, you have to give it the right defect name. Porosity means porous, but what is porous? Is it gas? Is it macro? Is it micro shrinkage? Is it oxides? All encompasses. So let's not talk about porosity. Let's actually call what the defect is. So we're now looking at micro shrinkage. We can see there's a small amount in the center section around the boss area. This is a prediction, and also in the gate, which we don't care if we have porosity in the gate because that gets removed. On the right hand side, again, we validated it. I have to apologize for this slide because we don't have the best facilities to do a dye penetrant. And when we did this dye penetrant, we had dust in the area. So those nice purple blobs or specks are actually dust that the dye, when we try to wipe the dye off with the developer, we caught. But there's no, I can assure you, there's no porosity in there. That's just particles that absorb the dust. And hence that was a free porosity casting. I'm saying porosity, but micro shrinkage. The second one I want to talk about in the case study is the Belisha Beacon Halo. One of our new customers came on board and wanted us to design the halo that goes round a Belisha beacon. Right, now this is a thin wall casting, and we had to think seriously. Obviously, we have to be competitive and we have to look at the design. Now, a lot of large thin wall castings in the past at Skaigh, we use a two-man pour to get the metal into the die. One of the criteria to get the price down was actually to do a single pour. So we just have one pourer to pour the metal. And we set ourselves some targets. So obviously, as I mentioned, to have a single pour, obviously we want to provide a casting that's defect free. We want to manufacture the casting as the highest quality we can produce. But on top of that, with my production head on, I want to produce as many as I can a day without affecting quality. Again, helping the customer get the part to the market quickly, which we did. And I don't want to be doing lots of trials. I want to make the die right first time. And that's the target. We want it right first time, hence using casting simulation. And out of all this, we want to reduce the product development cost. So we did a filling analysis. As you can see, it's a single pour down, a single control down sprue. We need to get the metal distributed evenly throughout the casting, so we have multiple gates around that casting. So yeah, it looks all nice and pretty, nice laminar fill, but we can go a little bit better than that. So one of the rules that we have in the foundry industry, we shouldn't exceed 0.5 meter a second. What you can look at is the velocity in the simulation. And what I want to illustrate here is that we didn't, as the metal got into the casting cavity, we didn't exceed that rule. So you can see a lovely laminar fill, all the gates and the metal meeting along the spoke. It's all nice and dandy showing this simulation, but I'm interested in a good casting. So we looked at the predicted macro shrinkage for this part. We had a shrinkage-free defect casting. This part is machined all over. On the right-hand side, we can illustrate we had a nice quality casting that we could ship to the customer. Right, the final case study I'd like to present is when you have a problem in the foundry. Right, and you've got to sort of strategize what we're going to do. Even though I'm an experienced engineer and foundryman, we all can be took back where we try things and they don't work. Hence, I like casting simulation, right? So we don't have the problem, so we can look at the method and the technique we've done. Now, like I said at the beginning, you can do the casting simulation, and if it's tuned in correctly, you know the technique's right. Because like I say, the operators can influence a good and a bad casting if you haven't done everything correct and put the right data in. And you've got to have the right pouring temperature, the right die temperature, and make sure for us as a gravity die casting, we use the right die coatings, have the right viscosity of the die coatings that are applied in the correct technique, right? So the strategy is analyze the filling solidification, pick the outcomes of the current technique. So we need to go out to the foundry and get the right data, and then determine how and why this occurs. So like I say, we'll do the simulation. We can resolve problems by redesigning the part. If we can go back to the customer, some customers are still where it's a tried and tested design and they won't change, but we do have a lot of customers who will willing to change, and we have to change the manufacturing method. And if we've found that our technique's wrong, we can redesign the technique and modify the tooling where necessary once we've done the simulation. Right, so what's the defect? Well, what we've got is we've got holes that appear surface and subsurface. So what I'm showing in that photograph there is the surface defects. I apologize, we seem to have lost the section of the one where we took it through the section, but it's of a similar ilk defect. So what we did is we did a filling analysis. This is a twin pour. This is a 35 kilogram poured weight. So as you see, the metal goes through into the pouring basins. To me, that looks a very good fill. Nice laminar fill, no turbulence, got the gates in the right order. So should be good. Let's look at the defect predictions. So we look at the macro. The casting doesn't contain any macro shrinkage. We are aware in some of the thin wall sections, we have some micro shrinkage. That doesn't cause a problem to the customer. And it looks excessively there, but on the cast sections, it's very minor. Really have to look under a microscope to find it. However, as I mentioned before, I want to look at the last air. Absolutely brilliant tool. I'll let this run a few times for people to analyze. So you're looking where last air remains in the die, which can get trapped as the casting solidifies. I'll give it one more time. Right, what we found on the predicted results is we were getting air trapped in that area, in that location. Like I say, I didn't have all the photos I could show you, but we were predicting trapped air on the left-hand side and on the right side, similar to the photograph I showed you originally. Right, we had to redesign the part to overcome that, go back and cut into the die, put larger fillets in the junction to allow that gas to escape. Even though there was a gradient on the casting, you would have believed that, you know, we wouldn't have entrapped air. Obviously, I have a limited time, so obviously I condensed a lot of what I was presenting, but there's lots of fields in Inspire Cast, like many simulation software packages, where you can look at velocity vectors, you can look at other result files and get similar results. Right, finally, to sum everything up, right, we give this software our approval. We've been very, very happy with it. Well delighted with this software. We love how the mesh is generated. I don't want to talk about other people's mesh. I'm not here to discredit or announce other people's software, but we really love the mesh generation. Remember, you've got to put good information in. Good information will come out in your results of your simulation. So it's helped us resolve casting issues that can't be resolved by our experience. Produces an interface between product design and casting process. What it does do, it increases customer confidence. We share these results with our customers. You know, we don't charge for them if we've made the die. If we've inherited the die, there will be a little charge. It aids a better understanding of the casting solidification and fluid flow. I'm nearly 61 and I'm always learning. And I think everybody's always learning. And this is a good tool to learn from. Helps in trying out theories without costly manufacturers have illustrated. There's lots of things you can do. You know, it's, you know, you learn the theory, you've got to put it in practice. And cost savings and reduced scrap and yield improvement. We're seeing that a lot. And we're always, with our customers, asked to keep the casting price down. Well, obviously we compete not with friends in England, but European foundries and China. And we try to keep the cost down to where we can actually make a profit, because that's what we're here for. Okay, that sums my presentation up, guys. Thank you very much.
Thank you for that, Mike. That's fantastic. Okay, so Tim, I'm just going to hand control over to you, and don't forget, for the people in the audience, you can ask your questions in that questions panel. Do please type them in, and we'll come to them in the Q&A session at the end.
Okay. Let me just have a little look. Have I got control? Organizer must close the poll.
Yeah, should be coming across. Tim, can you do that?
Brilliant. No problem. Let me have a quick look. Okay, are you seeing my PowerPoint at the moment?
Yeah. I can see.
Cool. Okay. Let me just have a quick look where I am. So, hi guys. First of all, thanks for the introduction, Pete. But I'll be now taking you through hopefully a very quick sort of method engineering workflow. First of all, I'd just like to thank Mike for obviously presenting. It's always, as I say, nice to see how the software is helping users in the real world, and obviously the success stories that they're having. So to begin with, just going to fly through a couple of slides, which I will just move on to the first one. So method engineering is obviously where we're coming up with the best method to fill the part, so hopefully we can reduce errors and potentially improve yields as well. The workflow will look something like this that we're going to go through. Generally, you'll have either designed your cast part or been sent the cast part. And the first step, always import it into the actual casting software. Once it's been imported, your step one could be purely a solidification only analysis. What this allows you to do is get a bit of an idea on how the part actually solidifies. Obviously, you know, based on the part, the shape, the size, your knowledge, you'll have probably a bit of an idea of how you actually want to fill the part. But just running a solidification only analysis can give you maybe an idea of the thicker regions, maybe best gate positions, best risers, feeders positions. One thing to note when doing a solidification only analysis is this is presuming the whole part is the same temperature and fully liquid. When it starts to solidify, so you only use this as a guide. In reality, we know that this isn't the case. You know, some areas may freeze before the part fully fills, and obviously we are going to get different temperature variations depending on number of factors and gate positions. This is just a little video. If it plays, let's have a look. There we go. A little video showing solid fractions, so the last liquid areas. So one thing we can see here at a certain stage is these two areas. If I can pause it at a certain point, the two areas on the right hand and the left hand side, we can see they're potentially thicker regions. You know, that could guide us in potentially riser locations. So we can use solidification results to guide us in our method engineering. Step two, you may just do a quick method, use the software very quickly to create some gate locations, add some components. In the image below, you can see that I've added 4 gate locations. I'm going to feed it from the bottom, and I've added some risers in the locations that the solidification sort of pointed out. Based on this, we are still seeing a bit of porosity, which we'll see in the software very shortly. And so another thing you could do, increase the riser size, see what effect that has. It does decrease the porosity, but not massively, and we are still getting porosity. So once you've gone through a few quick methods, you might refine your method. Generally, you'd probably design your final method in your preferred CAD system. You can do this in Inspire Cast, but you might be more comfortable doing it in your CAD system. And you basically are refining your method, and this is most accurately what you want to represent reality. So you want to make sure your filling conditions are all correct, things like fill time, temperatures, materials, mold temperatures. You want to make sure all that is as accurate as possible to get the best results. In reality, this could take a few more than 3 steps, but this is just showing you a bit of a workflow. So we can see here just a few of these parts filling, but I'm going to jump straight into a demonstration. I think that's the best thing to do for the next 10 or so minutes. Jump straight into a demonstration and show you the software. So I'm just going to just close this down or minimize it, and I should be able to share another screen. Okay, let me just monitor too. Are you guys now seeing my Inspire Cast?
Yeah, we are.
Yeah, brilliant. So jumped into Inspire Cast. This is the software. I'm not going to dive too deeply into the user interface, but basically you have your tabs along the top. You'll be familiar with the File tab. You've got your Edit tab, Windows shortcuts, your View tab, just how you wish to view things. We also have a Sketch tab, allows you to create some basic geometry, and the geometry tool to modify either the cast part or potentially create methods. The casting tab is where we spend most of our time, and this is our what we call our 5-step workflow. First step is to designate your cast part, and if you have a filling system, you can designate that and also set your gravity direction. Second step is to again create or designate any gate locations. Third step is to add any casting components. So hopefully you can see all the different casting components that we can add or again designate. Fourth step is to specify your casting process. So within Gravity, we do have investment casting and tilt pouring as well. And also we've got high pressure and low pressure. If I've got enough time, I'll show you a quick example of high pressure, but I don't think we'll be able to go through the full method workflow. And then the final stage is your run analysis. So here you can choose what type of analysis you're looking to run. So whether it be filling and solidification, or just filling, or just solidification. We can compute the deformation as well. What this means is we can predict residual stress and obviously the deformation of the part. Here you'll also choose your mesh size. So a general rule of thumb is in any wall thickness, you want at least 2 elements. So if you've got a wall thickness of 10 mil in an area, you probably want your mesh size at least 5 mil. So you've got 2 elements. There's always a trade-off between speed and accuracy, so just be aware of that. But we can do more advanced meshing where we can say, okay, if you do have a part that has thicker areas and then thin areas, you can say, okay, I want the thicker areas to be a larger mesh size, the thinner areas to be a smaller mesh size. Again, not going to dive too deeply into the meshing, but obviously if people have questions, feel free to ask them. But the first step in method engineering is to open a part. So just going to import a part. We can import a number of different formats. So whatever CAD system you use, we can most likely import the format into Inspire Cast. So this is my part that I wish to cast. And we're going to start with our 5-step workflow. So we're going to designate this is the cast part. So here we can choose our material, our grade of material, and also our temperature, pouring temperature. Just to show you quickly the material database. Again, not going to focus on this too much, but here we've got all our different standards, again, materials, and you can create custom materials in here as well, and all the properties. So I'm just going to leave that at default for this example. And I haven't got a filling system yet, but I can designate gravity. So you can see it is in the right location at the moment. If I wish to orientate it, I can pick a surface to align to, I can flip it vertically or just orientate it using a rotation tool. I'm not going to add any gates because I'm just going to do purely solidification. One component that I might add though is the mold. Mold's obviously quite important, depending on if I'm going to be doing a die cast or a sand casting part. Obviously, you're going to have different materials and thermal properties. I'm going to be doing a sand casting part, and obviously here we can specify our mold material, mold temperature. Again, your variables are quite important. You know, if you're doing a casting in December and it's freezing cold and your foundry's pretty cold and 10 degrees, you want to make sure that's put in because those variables will affect the results. I'm just going to leave that as default. So we've set up our mold. We don't need to go through any setup at the moment because we are purely doing solidification, but I'm literally just going to hit the run analysis tool. Here we can specify an element size. For speed purposes, I'm going to choose 6 mil, and I'm only going to do a solidification analysis, and I'm going to hit the run tool. This will go into the meshing stage. So the first stage is obviously to turn this CAD model into a mesh element. So it will be those 6 mil mesh elements. But I'm not going to wait here. This will take probably no more than a minute or two. But obviously, because we haven't got much time, I'm going to just Blue Peter style it, and this is the results. Hopefully you're seeing my screen and you're seeing the results. We're just looking at solidification, and in the video that we previously saw, we can start to look at potentially our solid fraction results, so last liquid areas. And as I say, these potentially might guide us in these locations. Clearly the part's not symmetrical. We've got a much thicker region here on the left-hand side than the right-hand side. But we can look at a number of different result types here in the solidification stage. Some of them might not be as valuable because if you're looking at temperature, and we can start to look at porosity, but because we're not actually simulating it filling, it is starting just from a purely liquid stage, all at the same temperature, and solidifying. Only some of these results might be useful if you're just purely doing solidification, but we just use it as a guide. Once we've done our solidification and we've looked at our results, we might then go back to the model and start to create a method. So this is just our status bar. I'm just going to I can just delete that, to be fair, but you can see it's pretty much nearly completed. Took a minute or two. I'm just going to delete that just so it doesn't slow anything down. And now you might start to come up with a method. So first things, I'm going to start to add some gates to the part. So I'm just going to just add some gating locations. And as I say, I'm going to fill it from the bottom. And I'm going to maybe add a number of gates around this profile here. I'm just going to just increase the size of this. I'll do one there. I maybe have one there. This time that'll need to be switched. And I'll do another one there. So I've added my gate locations. Now I might need to add some components. So I can go to my components tab. The first one we might add is a core. This clearly has a core. So I can click this tool here, and the software will automatically create my core for me. Obviously important if your core is going to be different material to your mold, so you can set that, and again set your temperatures. And the next one I'm going to add is a riser. So I'm going to let the software create my risers. These might not be how you may design them in reality, but this is just giving you an idea of how the part may fill. I'm going to change the size of them, and I'll put another one on that size. So I've added two risers, and I'd be happy now to do some filling analysis and see what effect this has and how this fills. So we can go into our setup now. If we look at basic setup, we are only just specifying a velocity or a fill time. This might be more than okay, so I could just set a fill time of 3. If you want a bit more control when you do create your method, you can obviously have constant liquid level, fill time, spoon height, flow rate, and as I said, we can also do tilt pouring and investment casting. Once you're happy with that, again we'll go to the results, and we'll click run. Again, we won't wait for those to be completed, but we can see here that I've already ran a couple of these, and I'm just going to look at the porosity because we haven't got much time, guys. I'm just going to look at the porosity for these, and we can see that based on this method, we're still getting a bit of porosity. This is based on smaller riser size, but then I did another run with larger risers, and if I just look at the porosity here, we are still getting quite a lot of here in this part, even with the larger riser sizes. So this is then when you'd go and refine your method, and let's just open up, rather than go through the whole setup again, let's just open up the results for this one. Let's just open up this one. So this is the final method. So you can see you might have designed this something like this in your CAD system, and we can just quickly go through the results. So with this one, there was 3 methods that we went through. One you can see here with symmetrical riser sizes, and you can see here, if we again look at the solidification results, obviously the main thing I'm focusing on here is trying to draw out this porosity here. We can put some call outs on it, and we can look at total shrinkage volume. And we can start to look at that volume. I then obviously changed the method and increased the rise size on the left-hand side ever so slightly. Didn't have too much of an effect. So another thing I did then was added another component, added some chillers to the part. So you can see here, if I just turn off the results, we've added some chillers in the third method to see what effect those would have on the part. And now if I look at my porosity, we can see we're getting a very, very small amount in this area. Might be passable, but we're getting a very, very small amount. We can look at, again, that shrinkage volume, and we can obviously put a measurement on it and see whether that's acceptable. But again, we could go one step further, and most likely we'd be able to remove all the porosity from the part if we kept on going another step forward in terms of method engineering. So that's just a very sort of quick workflow. Sorry, I'm sort of rushing through it, but I haven't got as much time. One thing I'll just very quickly show you again is a high pressure one. This is sort of two methods. This is the first method, where if I look at the filling, and I'm just going to just press play, so we can start to see how this part fills. So this is again another example. We were going to spend 10 minutes on it, but we haven't got as much time seeing how this part fills. Obviously, in this stage, things that you might be interested in is last air. You want to be making sure potentially the air is in the overflows, and we can start to look at the airflow as well. So you can start to look at, if I just press the play button very quickly, start to look at airflow, so we can start to see where we might get defects. We can see here that we are getting defects there, and that might cause problems. So then again, you might go and change your method. This is potentially the final one. This has got some cooling lines added to it as well. The gates have been increased. We've got another overflow in the middle. The angle of attack, the angle of the gates may have changed as well to get a better flow. And again, I'm just going to just hit the play button. We'll just have a little look at how that one fills. We can see how that part fills. And again, this is high pressure. Haven't got too much time to go over all the results with you guys, but in terms of high pressure, just to show you the setup and what we'd be using once it loads. Why isn't that loading? Let's have a quick look, see if I can load it on the other one. There we go. So hopefully you can see this. So you can use obviously your shot sleeve. You've got all your machine parameters and your piston control, and you can add variables. You can also compute clamping forces and that sort of thing. I was going to show you a bit more on high pressure, but we haven't really got enough time. I do want to leave a couple of minutes for questions, and I don't want to go too much over the hour. So that's sort of where I'll end it. Probably pass it back to Rob just to finish up, and if we've got questions, we'll try and answer them as quick as possible.
Thanks, Tim. Thanks, Mike, as well. Hopefully that gave you a quick idea of how easy it is to set it up in terms of the simulation. It's quite a simple workflow. I don't think we need to go back to slides. I did have a couple more slides, but I think we will shoot straight to questions, Pete. But before we open up for questions, if you do want to spend more time with us, there are several ways in which we can do that. The first way is through a more tailored demonstration where we have a bit of a look at one of your parts. We work with you to run the simulation. With any luck, you can start to potentially use simulation to replicate problems that you might have experienced previously in some of your production runs. So we can do it through a demonstration, and then we typically follow that up with some sort of trial. So we're very happy to support you through a sort of trial where we'll provide some consultancy and some help in terms of getting set up. The other thing that we can do is help you with business cases as well. So Pete, thanks. You read my mind. I think there's a poll up on the screen now. So if you do want, we will follow up with you anyway and find out sort of what you thought. But if you do specifically want some in terms of a trial or potentially some costs or a demonstration, then please fill in that poll, and I'll probably be the one that gets in touch with you following that. So we'll just let you answer that, and then Pete, I think I shall pass over to you in case there are a couple of questions before we finish up.
Yeah, absolutely. So thank you, Tim, and thank you, Rob. So we're just going to leave that that question on screen here while we start taking a look at some of the questions that have come in. So just to kick us off, Tim, probably one for yourself, but perhaps Mike can jump in here as well. So what would you say is the average sort of simulation times we're looking at here, and when you've been doing some of these casting simulations?
So it really will depend. As I mentioned very briefly, there is always a trade-off between sort of speed and accuracy. And generally what this means is if you're running with a larger mesh size, it's going to obviously take quicker. If you're running with a finer mesh size, it's going to take a lot longer. But it depends on a number of factors: size of the part and generally your mesh size. So I've seen simulations in Inspire Cast run for half an hour and you're getting good results. but that might be in a fairly small part and not complex part. But then you also get very complex large parts that you might be running for 4 to maybe even overnight sometimes. So it's very variable.
Yeah.
I'd add to that, Tim. I'd also talk about the hardware you're using.
Yeah.
Obviously, if you've got multiple cores, I think we have 7 cores on our processor. So we set the software to that, and you're right again, it takes from 20 minutes to several hours to run a simulation. And like if you went through the training, you'd start with a coarse mesh, which is very fast to give you an indication. And then when you want to fine tune it, you run it with a finer mesh.
Yeah, that's correct. Yeah. So so number of variables, hardware and mesh size and size of parts, really, that's what I'd say.
Okay. Okay. Is a question here? I mean, is there any sort of minimum spec of machine that you'd recommend, Tim, or maybe that's some information we could send out afterwards? But
Yeah,
is there any
there are
minimum
minimum specs, but yeah, we'd happily send those out separately. But we have there are minimum specs, and there's also specs that we'd recommend personally. So we would happily send out hardware specs separately.
That's great. Quick question here, which I can answer very quickly, which is just a question about recording and has there been recording? There has, and we will make sure you get a recording so you can rewatch this or share it. That should be with you tomorrow. There's a question here, a little bit of a longer question, and I think this might be one for yourself, Mike. So I'll sort of read it out. So when you see shrinkage within a ingate cavity, as you presented in the example in your die, will you not see shrinkage pulling sometimes into actual casting cavity? Is the simulation that accurate with location predicted shrinkage?
Yeah, it is. It's pretty good. You can see across the casting ingate interface where you can get shrinkage. Obviously, it's good data in, good data out, as long as you've got the right data. But we've found where we've moved shrinkage location to a non-sensitive part, because not all castings can be shrinkage free. You know, you've got a machine that are a solid billet, but because there's always a cost to everything. But we design, and there's no secret in gravity die. You want the gate to have a lot of surface area, and you want to get that to solidify prior to the runner system. If you're not careful and you have a large fixture ingate, then obviously the casting becomes the feeder, and you have a lovely, nice sound runner system. So you've got to use what you've been taught or what you've experienced, but you want a lot of surface area so you can chill that gate off very, very quickly, so it doesn't influence the casting soundness. And if you do it right, it can also be advantageous, where it can act as a chill and create a directional start in front of solidification. I hope that answers you guys.
Thanks for that, Mike. One question here, which I think maybe I can expand on a little bit, is just, at the start of the webinar, I think we had around about a third of the audience who had not really explored simulation, particularly for casting. Is there any advice on your side, Mike, about taking a step towards using simulation? Any sort of advice you'd give to organizations who are maybe looking at it but haven't actually taken that step before?
Well, you have to go back to training. I mean, I started at 16, and I had peers who was well trained in metallurgy, well trained in design. I was a lucky person at the time, a lucky student, where I had people who could teach me their experience. I'm sad to say we don't have that. I mean, sorry, I have to go back. There was 2,600 and something foundries when I started in the foundry industry at 16. God forbid what we've got in this country now. But I know that the ICME, they use Magmasoft. It doesn't matter what software you're using. They're starting at a very young age by teaching young foundrymen, foundry technicians, engineers to use the correct tools. I mean, I can't understand the foundry why they don't use the simulation. It's never, I know I hear the term a lot, it's a black art. To us foundry engineers who have been in the industry, maybe if it was a foreman and he experimented, he wasn't a black art. He was doing experiments out there. You know, he had knowledge. It was never some sort of magic art. You know, he knew how casting solidified. I hate the term black art, but for the younger generation, you've got to have this software because, you know, it's like a pattern maker. If he needs the latest CNC machines. In the olden days, you'd give him chisels to carve out a wood. It's only like for a methods engineer or technician, you've got to give him the tools to provide a good service. And again, he needs to be out there on the shop floor. You know, it's all right being in an ivory tower running a piece of software, but you've got to be out there feeling, if you're in a sand foundry, feeling the sand, finding the temperature, is the moisture in the sand. There's lots of variables out there, and you only can plug so many into the simulation software. But to end it all, you've got to use it in the foundry industry. It's the way forward. It always has been. Like I say, I've used the software for, I was counting it up, about, where did I write it? 28 years. I started using casting simulation back in 1994. And you never look back once you've used it. I hope that answers you guys.
That's great, Mike. Thank you very much. And you know, I do sort of appreciate here we are a little past the hour, so I'm going to sort of draw the webinar to a close. Just quickly, a huge thanks to Mike, obviously, for coming on, giving his thoughts and experiences with simulation tools, and also with obviously some of the Altair tools that Mike's implemented with Origin. Big thanks to Rob and to Tim, of course, as well. And a huge thank you to everyone who joined us on the webinar today. Hope you found it useful, interesting, and of course, as Rob said, we can be in touch with you, or the Origin team can be in touch with you to answer any further questions you might have, set up any of those trials you indicated you'd be interested in. And yeah, hope to see you, you know, exploring the tools very soon. So big thanks again, and we hope to see you on a future webinar, and we'll speak to you again very soon. Thank you.
Thank you, everyone.
Thanks, everyone.
Yeah, take care, everybody.